Thank you for the opportunity to give you this talk. In this talk I will summarize of our work on FPGA All Digital Transmitters, and it is a different way of looking into the design of RF transmitters. So we try to push as much as possible to bits closed antennas, so which means that the digital processing is pushed as close as possible to the radiating element. So this is the university where I work, the research institute where I work. I belong to University of Aveiro and Telecommunications Institute. They are both located in Aveiro, that is a city in the coast of Portugal, in the Atlantic coast. This is a photo of our campus, and this is our group. We have a considerable number of members between staff, researchers, professors, master students, PhD students, working on radio systems and related topics. Now moving into the agenda of this talk, after providing some scope for this work, I will summarize the very basics of all digital transmitters, and then I will summarize some contributions we did over the last 10 years on some different topics on this research domain, and then I will conclude with some remarks and some open issues and future work. So, starting with the scope, it is well known then mobile communications and communications in general are always evolving. We have a considerable increase on number of devices. Only cell phones by itself are increasing more or less 7% in a year. We have higher data rates. We have increasing data rates. The traffic we generate is also increasing considerably. There is continuous requirements to decrease the latency on communications. We need better network reliability and also better coverage. So, and to address these issues, these challenges, there are several technologies that are being developed, either in scope of 5G and beyond, and it is expected that beyond 5G we will move to higher spectral bands. We explore more aggressively MIMO and MIMO communications. We have more diverse, more challenging communication environments. We will non-terrestrial communications based on CubeSats, UAVs and satellites will be more available everywhere. We will use different types of communications in order to save energy, for instance ambient backscatter communication, in order to have more efficient and more autonomous devices. Radio front ends needs to be more flexible in order to, for instance, to cope with different spectral bands, in order to share spectrum dynamically. Network automation, in terms of network management automation, will also be a need, and to manage all these things we are starting exploring, the community is starting exploring artificial intelligence in order to manage all these things more in a more convenient way. For beyond 6G, even more advanced topics such as quantum communications, Internet of Bio and Nano Things and other topics are also being explored. But the challenges for 6G are already large enough. Let's concentrate on them. Possible approach to deal with these challenges and with these requirements is we need more agile, more flexible devices, and in my case, in our case of our group, we are much focused on radio transceivers. One way to achieve that is to increase the digitalization and adopt even a higher degree the software-defined radio approaches. We need higher system-level integration, and also probably in order to cope with some challenges, to perform also some cross-layer optimizations. We need better energy efficiency and explore AI and machine learning in an efficient way, which is something that is still to be proved, that needs still to be proved. But let's start from the beginning, so from the very basics, in order to establish a timeline until the work we developed over the last 10 years. So at the beginning, what we had, what is the architecture of a classical RF transmitter? Basically, if we consider that the processing is done at baseband, we have the DACs at baseband. All the remaining functions are performed by the analog domain, namely the filtering, the conversion, the amplification, and radiation. This is a well-established, very mature RF transmitter architecture. It is mature, it has low complexity, it is low cost. But the integration is difficult because the technologies for the analog part and for digital part are very different and not easily integratable. And also this approach has also huge limitations in terms of multi-band and for instance multi-carrier approaches. Then transmitters evolved, and if we perform the radio processing in the digital world until RF, which means that all the baseband, all the conversion is performed on the digital side, then the DACs are placed at RF, which means that they are sampling the signal at the frequencies at the order of magnitude of carrier frequency. Then only the filtering, amplification, and radiation is done in the analog world. This architecture has the advantage of being more agile, wideband, and also supports naturally multi-band and multi-standard capabilities because these features can be handled efficiently on the digital domain. However, they are high cost yet. Some solutions start to appear, but they are still high cost. The power consumption of high sampling rate DACs is considerable, and scalability is also something that needs to be proved. We have solutions, integrated solutions based on this approach with, I would say, 8, 16 DACs, but how it would scale to a large number of elements in order to be able to cope with massive MIMO systems is something that needs yet to be proved. So these are the summary of the classical RF transmitters, first with DACs at the baseband and then at RF. The truth is that radios became much digital. So most of the most of processing on radios became digital due to the concept of software-defined radio. And in fact, SDR, software-defined radio techniques, already play an important role in the radio hardware design. This is a picture of the typical system. So basically on software-defined radio systems, we have bits on one side, we have processing, we have the data conversion to the analog domain, and then we have the amplification and radiating element. The ideal architecture can be achieved if, of course, the DACs are placed at RF level to allow all the digital processing to be in the digital domain. 10 years ago, we start thinking, because our background, me and my students at that time, were mainly on the digital side. We used FPGAs very extensively for different purposes. At that time, FPGAs start to have available what we call multi-gigabit transceivers. They are basically transceivers that provides the support for the implementation of high-speed serial links. And we thought, what about if we apply pulsed modulators, namely delta sigma or PWM, to the design of radio transmitters. The idea appeared challenging because when we apply pulsed modulators to a processing for the analog conversion of a digital signal, we need a considerable oversampling ratio, and if we are talking about radio signals, we will have to deal with considerable high frequencies. While in audio processing, this is something that is well known, is well natured, because of the operating frequencies are much lower. In the case of radio frequencies, this idea of applying pulse modulators for the digital to analog conversion of radio signals became at that time challenging. But in any way, we start this effort, and in fact, after years, I think that we made some interesting contributions. Okay, that's exactly those contributions that I will summarize on this talk. So let's start with the concept. In an all digital transmitter, basically, we don't change the way the modem is implemented, so the baseband processing is exactly the same. What we change is the way we convert the signal from the digital domain to the analog domain. And for such purposes, what we need is a high-speed serializer that takes the samples produced inside the FPGA or inside the digital device in general, and puts them on analog world in order to, or outside the device, in order to support efficient some kind of pulse modulation. Well, if we have the capability of output a high-speed pulse modulator, either sigma delta or PWM, then what we have to do in order to be able to radiate this signal is to either amplify it and then filter, or vice versa, filter and then amplify. So if what changes in one approach or the other is that if we use the amplifier first, it must be a switched mode power amplifier able to cope with a two-level output of the digital device, and then filter, of course, otherwise we'll have lots of quantization noise sent to the radio link. Or if we put first the vice versa approach, if we swap the filter and the amplifier, we put filter first, and then we can use, I would say, any type of amplifier, including linear amplifiers. So the idea is to use a two-level of output of the digital device, either delta sigma or PWM based. We push the processing closer to the antenna, which gives us more flexibility and agility. It can simplify the front end because we avoid at all the traditional DACs, which can result in lower costs, lower size, and more scalability. To give you an idea, this is the reality now, not 10 years ago, but now, for instance, it is common to have FPGAs, or in fact RF SOCs that also include FPGAs with 8 or 16 DACs, but the same FPGAs can include dozens of high-speed serial transceivers, which means that if I want to create a transmitter with, for instance, 32 or 64 outputs based on this approach, it is feasible. The same number of outputs with traditional DACs with the current integrated device is not possible at all. There is also a potential advantage of this solution is that following: it can be more power efficient, but of course this is something that we believe because we are not using high speed gigasample per second DACs, but this is something that could be true but needs still to be proved. We need to perform a careful comparison in order to prove this claim. Now a little bit more details about implementation of the digital transmitter concept. So the idea is to digitalize the whole RFTX chain until the output that is applied to the filter or to the amplifier, no external DACs, so because everything is based on pulsed modulations. This allows all the radio data path to be digital from baseband to RF, and it can be embedded on a single device, and in our case, of course, we are talking about FPGAs, but the same approach can be also applicable to ASICs if we want to build we have a use case to build the ASIC. The external RF interface I was already mentioned is based on multi-gigabit transceivers. That, just to give us some more information, multi-gigabit transceivers are the digital transceivers integrated on FPGAs that support, for instance, the implementation of the SATA interfaces, PCI Express, high-speed Ethernet, USB. So these are generic parameterizable transceivers that support the implementation of these high-speed serial interfaces, and in fact, to be honest, we are using them out of specifications. We are using them for an application that the manufacturer did not thought about when it decided to integrate these blocks on the FPGA. Okay, but we found a different application for those transceivers. As I mentioned, the external components are basically the amplifiers, filters, antennas, duplexer, the RF switch, what is needed in order to implement the traditional RF chain. In this picture, it is shown exactly this structure. So starting with baseband, then we need to perform in digital world the up conversion and pulse encoder or modulation. The order affects if we perform first the pulse modulation and then the up conversion, or vice versa. It affects the challenges and also the flexibility of the circuit, but I will talk about that later. Then we have the transceiver, that is basically in transceiver after a high-speed serializer, and then we have the remaining components. As I already mentioned, for the pulse encoder, so for pulse modulation, two approaches can be used. The first one is the pulse width. Basic conceptually, what we do is the following. So if okay, so no, I cannot use the laser pointer here. It's because I have two screens. So if Rn is our signal to transmit, in the pulse width modulation, conceptually, it is compared with a triangular wave. It generates a PWM representation of the signal, which means that we'll have the desired signal as well as the quantization noise that here is in terms of harmonics. To send the signal, we need to filter the harmonics and keep the desired signal. So this is the typical spectrum of a PWM signal. So at the center it is desired signal. Around the desired signal we have the harmonics. If we filter the harmonics, we have the signal that we want to transmit. This is a conceptual picture. In fact, the same PWM can be generated by a lookup table. If we have the lookup table, which size depends on the PWM resolution, I can input a digital sample and the lookup table gives me immediately the representation of the signal in PWM. And this is, of course, a much easier way to implement in the digital world. The other alternative is the delta sigma modulation. Here, different topologies can be used, but in any case the idea is the following. So we have a typical delta sigma. The delta sigma tries to, due to the noise transfer function, this is an ordinary delta sigma, I will not enter into details, but the idea is due to the noise transfer function we will apply, we try to remove the quantization noise away from the desired signal, which means that we have the desired signal at the notch of the noise transfer function, and then we have the quantization noise around. Again, to transmit this signal, we must keep the desired signal and filter all the quantization noise. For instance, there are some things that we can do in order to simplify filtering. We can improve the sampling frequency of the delta signal, which means that improving the oversampling ratio. We can use higher order delta signals in order to try to move away the noise from signal. But these are all techniques that can be explored. As I already mentioned, the delta sigma or the PWM and the digital up conversion can be placed one after the other using two approaches. So I can, for instance, place first the pulsed modulator and then perform the up conversion, which is shown in this slide, or vice versa, which is shown in next slide. In this approach, which means that the pulse encoder, either the delta sigma or the PWM is placed at the baseband immediately after the modem, and then followed by the digital up conversion. It has the advantage of being simple because that delta sigma operates at a lower speed. It can be easily implemented on FPGAs. However, it has a lower OSR, oversampling ratio, because delta sigma is applicable to baseband, and we must account for the up conversion factor we need to put signal on the carrier frequency. Which means that besides it is simple implemented on FPGAs, it has low oversampling ratio, it has limited agility and multiband capability. Why? Because since the agility is determined by the flexibility we have at baseband, when we convert the signal to the carrier, basically the agility, which means how the granularity of the carrier frequencies that I can select is degraded. And also there is, with this approach, there is a strict relationship between the frequency at the baseband, the oversampling ratio, the upsampling factor, and also the carrier frequency, so the frequency of the transceiver. So there is I would say, a tricky relationship that basically degrades the flexibility of the approach. The other approach is to change the order. So perform first the up conversion after this baseband modem, and then to perform the digital up conversion. Here we have more flexibility, we have more carrier agility, we have higher oversampling ratio because the delta sigma is at the carrier frequency. However, the delta sigma or the PWM itself is much more challenging because it must operate at the order of magnitude of the carrier frequency. So it operates at higher frequency, so the design of the circuit is more challenging. When we started this work, there were only alternatives, there were only implementations using this approach reported on ASICs, no reported works on FPGAs. So these were the very basics regarding the approach, regarding some trade-offs. What was the question? What was our question that has driven this work? Can all digital transmitter architectures compete with figures of merit of their counterparts, namely radio frequency systems on chip, in the context of some beyond 5G systems? Be aware that I'm not claiming that this can be used for all purposes, but in some situations, in terms of carrier frequency, in terms of bandwidth, in terms of scalability requirements, this can be an answer. Does not solve everything, of course, but this can be an interesting answer due to the scalability and due to the capability of implementing a huge number of transmitters on a single device. What I will briefly summarize next are our contributions, the challenges we addressed over the last 10 years. Starting by the relaxing of the analog filter requirements. So we have either independently if we use PWM or delta sigma, we will always have our desired signal and we have noise around that needs to be filtered. If I move away the noise from desired signal, it simplifies filtering, as you easily understand. So, and one of the approaches we used in order to move away move away the noise from desired signal is to use this approach. So, we divided the pulse modulation into stages. One stage is a multi-level delta sigma, because a delta sigma can be two-level or multi-level. When we use a multi-level approach, the result is that the quantization noise lowers. So we use the first stage, that is a real-time delta sigma that operates in real time, but multi-level, with a better, with a lower noise around the signal. And then we apply the output of this stage to a two-level delta sigma, but in fact this delta sigma is based on a lookup table. And since it is based on a lookup table, in fact it is an approximation of a delta sigma. So we compute the delta sigma offline, then we store it on a lookup table, then since this, I would say this delta sigma with quotes operates in such a way, it can operate very fast, which means that we will increase the oversampling ratio, and this will move away the noise from the noise was already lower, and with this approach we move the noise away from signal, which means that in practice we have our signal of interest that would be more easier to filter. So this is the approach. This is our setup, our lookup table, and our block diagram. So in fact we built a test bed in which the first level we have three different options: a 2-level delta sigma, a 11-level delta sigma, and then 100 more or less level delta sigma. These numbers sound strange, but they are related with the size of the lookup tables that are put on the front of these delta sigmas. Then we have the lookup tables. We also used dithering in order to distribute noise. Then we perform the up conversion, we apply to the MGT, and basically the MGT output so serializes the high speed bit stream that results from this processing. Here is our laboratorial setup, and here are the results. Here we can see that as we move from a 2-level to 11-level to 101 level, the noise becomes each time lower and away from desired signal. For 11 levels, that is some I would say the middle, the values in between. You see, for these sample rates, 3, 15, and 31 sample rates, the EVMs of the QAM signal we obtain are very reasonable, considering that we are output a digital signal from the FPGA without any DAC. Now let's move to the next topic. 5-6 years ago we had an idea that what about if we implement multiple all digital transmitters, because we can do it on a single device, in order to drive an antenna array with several elements. And the approach is the following. So we have our all digital transmitters that can drive the analog transceivers, mainly based on amplification, filtering, and then we have the antenna elements that will radiate signal. So the idea is to develop high integrated transmitters for antenna arrays. We have N all digital transmitters. We included on the digital processing both the amplitude and phase tuning of transmitters. We did that with digital multiplications and coding, so everything that is related with gain and phase is done digital. This allows us to perform beamforming techniques fully integrated on the device, and this technique scales very well to a huge number of outputs because of high availability of MGTs on the current devices. But since we have multiple outputs and there can be mismatches in terms of delay, we also have had to develop calibration techniques in order to be able that the beam is aligned to the direction we want it to be. So this is an outline of our setup and of our system, and also a photo of our setup. We are using the transceivers at 10 gigabits per second. At that time was a common value. Now we have transceivers 3, 4, 5 times faster. So in between we did not upgrade this approach to the latest transceivers, but it can be done, and it will allow us to move forward the frequencies we can achieve. The carrier frequency is 4 times slower, and this is a typical value of these transceivers. Typically, when we can reach carrier frequencies that is a quarter of the bit rate of the digital transceiver because of the way we perform the digital up conversion. Then we have an 8-element microstrip antenna. We have implicit filters on antenna elements, and we did the experiments of our anechoic chamber. And in this picture we can see that we have the baseband, then we have as the number of transmitters corresponding to the number of antenna elements, because each transmitter drives a different antenna element. Each transmitter itself follows a multi-phase approach, because we can, in a digital transmitter, we can have just a single phase, which means that I have just a single path on delta sigma, just a single path on PWM, just a single path on digital up convert, or I can divide the circuit in multiple phases in order to allow parallel processing of each phase in order to reach equivalent sampling frequency higher than the clock rate I have to clock each phase individual. For instance, if I have a phase operating, for instance, at 100 megahertz, if I have 16 phases, I have equivalent sampling speed of 1.6 gigasamples per second, because all the phases work together, because I split the data, I split my bit stream between several phases. So basically this is our setup, and these are the results. We have performed some experiments with different sample rates, from 3 again to 15 samples per second. Then we performed also some experiments in order to see if we can steer the beam correctly, and we realized that without calibration we achieved on the left picture, we achieved the radiation diagram with the gray line, so there was a little deviation, but when we performed calibration procedures, we obtained the expected radiation diagram, and we were able to tune from minus 40 to plus 40 in terms of azimuth our beam using just this digital approach. Now let's move forward. The next contribution we did was in order to achieve an agile modulator. Agility here means how small or fine I can move the frequency of the carrier. And as I already mentioned, the order of the digital up convert and the pulse encoder or the pulse modulator affects. And what we did here is to swap. Instead of having the pulse encoder before and the digital up conversion after, we swapped. Of course, it makes the design more difficult, more challenging, because the pulse modulator, either delta sigma or the PWM, will operate at RF speeds. But in this case, we will have a higher oversampling ratio, and then we have a better control of the carrier frequency. We changed the order of the blocks, and for the pulse encoder we used two approaches, either PWM and also delta sigma. Again, in order to cope with high sampling rates of the system, we used a polyphase or a multiple phase implementation, in which multiple delta signals, multiple up conversions take different chunks of the same signal in order to achieve equivalent a higher sampling rate. This is the block diagram of our setup. Again, the base band is always the same. Typically in our case a QAM, OFAM, some kind of representative baseband. Then we have the polyphase interpolation that will allow us to generate multiple phases for the same signal. Then we place the parallel digital mixer that basically perform the up conversion. So every sequential sample of the signal is applied to a different phase of the up converter, and then we have a polyphase DDS that has the basically a representation of the carrier frequency in multiple phases. Then we placed the multi-core DSCMs and also the implementation of PWM, and we are able to switch in our test bed between one modulator to the other in order to get the results. And here are the results. In the case of PWM, we can see we performed two tests for 6 MHz and for 12 MHz over a range of carrier frequencies between almost zero, almost here means a few hundred megahertz of carrier frequency, up to 6 gigahertz of carrier frequency. As you can see, the EVMs obtained for our modulated signal are perfectly reasonable. We are always below, I would say, 3% of megahertz, of 3% of EVM, sorry, and most of time below 2.5% of EVM. With this approach, we have a carrier agility of 1.5 megahertz, which means that we can tune the carrier in a very fine-grained approach. The maximum bandwidth was at that time. Meanwhile, technology evolved, and probably with current device, with current technologies, we can achieve even better results. These are similar results, but for delta sigma. Again, we tested for the carrier frequency between 100 MHz up to 5 GHz.12 with a carrier resolution of 1.5 MHz. We test with a maximum bandwidth of 48 MHz, and again the EVM values for such an approach are perfectly acceptable, always below about 3%. Then we move to another topic, that is, what about if we try to increase the bandwidths that our system is able to handle in order to achieve a real wideband transmitter. So this mainly involves to improve the bandwidth of our delta sigma. The approach was the following. So we want to achieve, the target at that time was to achieve a bandwidth higher than 480 MHz. That was the state of the art at that time. We used an RF stage architecture, which means that we are putting the delta sigma at RF, not at baseband. we added 3 zeros to the noise transfer function of the delta sigma. It has several stability issues. That's why we used several outputs in order to have a multi-level representation and to ensure stability. And basically we divide, in order to achieve high sampling rates, we split our delta sigma in several, and we divide the input samples by the several delta sigmas, again in order to achieve a higher equivalent sampling rate. At the input, we split the samples between delta sigmas, and at output we join again. So at input we do what we call the interleave the samples, and the output we interleave again the samples in order to have a high sampling rate signal that can be then serialized and put externally. This is the block diagram of our setup and also the laboratorial setup. Again, we use at that time 10 gigabits per second. We use 7 MGTs that are combined externally by a power combiner in order to get the signal. In fact, in this case, the delta sigma will use a multi-level representation in order again to achieve stability. We need to balance the paths in terms of timing, because since we have multiple paths, any mismatch will degrade the signal, and it was also in terms of balancing delays, they were balanced using different delay lines, and as a result we were able to reach 1.25 gigahertz of bandwidth, which is a considerable bandwidth for something that is done entirely in the digital world and pulsed modulator. This was the limit we achieved at that time. If we are able to build a custom chip in which we control very carefully all delays, this is a promising technique, because we had to add fine-tuned delay lines at the output in order to balance, but if this is all integrated, I think that we can achieve interesting results. So these are promising results, and for bandwidth between 300 MHz up to 125 MHz, we can reach again very interesting EVMs between 1 and 2%. We also worked on this type of transceivers allowing transmission in multiple bands, which means basically the following: we had to create delta sigmas with several notches, in the notches in noise transfer function, of course, and in each notch we are able to send or to transmit a particular signal. So this was the approach. Again, we used multi-core delta sigmas. We used several noise transfer function zeros, as I mentioned. We integrated the digital up conversions inside FPGA, and again we needed to, in order to achieve the desired speed, to split our sample, all our baseband samples through the several delta sigma phases in order to achieve higher sampling rates. So this is again the block diagram of our setup. What they have in common is that they all consist on a baseband, they all consist on a polyphase representation of my signal, they all consist on polyphase up conversion, and also on the polyphase delta sigma. What really varies is the type of delta sigma, how we play with zeros, with poles, how we then apply the output to the MGTs. In this case, for instance, we can use either one MGT or we can use several MGTs, again to have several outputs in order to reach a higher signal to noise ratio, in order to decrease the quantization noise of our signal. These are the results with a two-level output, which means using just just one digital output, 2-level output, and also results with 7 levels. So if we combine several digital outputs, we will have a multi-level representation of our signal, and in this case what we can see here is in both cases we see that we have 3 notches. We see that we are able to transmit 3 signals simultaneously, but when we use more outputs, the quantization noise lowers considerably, and the results become better. In these pictures, again, just to give an overview, we have the EVM measurements for each carrier we are transmitting simultaneously, and again, as you see, the EVM measures are relatively good, again between 1 and 2%. But using an adequate delta sigma topology, we prove that it's possible to integrate on a single transmitter the capability of having a multi-carrier signal. And finally, the last contribution that involves basically exploring the higher order modulation of current FPGA transceivers. In the past, and currently yet, most of the FPGA transceiver, digital transceivers, are 2-level transceivers, which means non-return zero transceivers. But to achieve higher bit rates, the transceivers start to become PAM4, which means that each symbol can have 4 different levels, which means that each symbol can carry 2 different bits. Since we have a multi-level, so multi-level means more than 2 in this case, multi-level transceiver, we can benefit from this approach in order to have a multi-level output, and in this case to have a lower quantization noise. So that's why we are exploring in the scope of this transceiver, and we believe as the transceivers will evolve in terms of order of modulation, we can still move forward this approach in order to achieve even better results. From our perspective, using a PAM4 transceiver instead of a non-return zero, what will lead directly is an improvement on the coding efficiency. So the quantization noise will lower, which means that the power out of band will lower, which means that the ratio between the power of signal and the total power will improve. As a result, the coding efficiency will be higher. Of course, we will not have a 2-level signal anymore, but with this coding efficiency will be improved. The good news is that we don't need to change almost nothing in our approach. Delta sigma will be nearly the same. We are just changing the number of output levels. All the remaining blocks will be kept the same, which means that in terms of logic resources, if we compare a non-return zero, so a non-PAM4 transceiver with a PAM4 transceiver, we basically have nearly the same resources. The percentage of flip-flops, lookup tables, DRAMs, DSP slices, the number of transceivers is basically the same, because we are benefiting just from the 4-level output of transceiver. This is a photo of our laboratorial setup, and these are the results. In orange or red, I think that this is orange, but my students say that is red. I think that is orange. In orange is represented the results of the non-return zero transceiver. In blue, it is represented the results. The results here means the spectrum of the PAM4 transceiver. As you can see, there is a significant decrease of the noise, of the quantization noise of delta sigma, and also there is a slight gain of the power of the signal to transmit. And on the right side we have the EVM measurements for the PAM4 setup, which are quite interesting. And we also measure the coding efficiency, and just changing the type of the transceiver allows us to increase the coding efficiency from 5.8% to 63.2%. Now the conclusions and the open issues, future work. So the work I briefly summarized here because I skipped most of the details. My intention was just to provide an overview of what we did with this approach, but most of work I have shown here was focused on design and optimization of all digital transmitters, all FPGA based. We believe that all digital transmitters based on this approach may present solutions to some of the RF DAC shortcomings. They have lower footprint, they provide good signal to noise ratio for not very high bandwidths, and they are, as I already mentioned in the beginning, potentially more power efficient. But again, this requires, I would say, this requires more study, and in particular, it requires to put together the entire chain, the all digital transmitter, the filter, the amplifier, and measure all together. Okay. These are a summary of our contributions. So, in first contribution, we reduce considerably the out-of-band noise around the carrier frequency, allowing us to relax the filter requirements. We proposed the first real and complete system where an antenna array was driven by an all-digital transmitter. We were the first at that time to have an agile transmitter in which the pulse modulator is done at RF, which allows us a fine-grained control of the carrier frequency. We were able to transmit very wideband signals. We allowed concurrent transmission, in our case up to 3 carriers using just one all-digital transmitter, and we were able to test with successful PAM4 transceivers in this scope. For the future, is our intention to explore. There are still some digital optimization techniques in terms of arithmetic, for instance, that could be improved in order to achieve higher sampling rates and consequently higher bandwidths. We want to also to test some of this approach with more recent transceivers that are either faster or provide higher order modulations. And it is our intention also to integrate this work with in 3 different ways. First, with optical components to increase carrier frequency, and also, for instance, to allow this work to be used in scope of the front-haul in Cloud Run networks, because we are talking about transport of digital signals over fiber, and the way we put signals externally, they are all already well suited for fiber transmission and to provide naturally the support of radio signals over the fronthaul. We would like also, and this is very, very important, to integrate with different types of PAs in order to have a complete assessment of the efficiency of the system and the power efficiency depending on types of PAs, and also, to be honest, in order to have a system that is really agile, is not only the digital part that needs to be agile, but also the filters that are outside. So we need to integrate with tunable filters that would allow us to filter everything that is not signal, that every noise that needs to be filtered before radiation, in order to have a complete assessment of the capabilities of our approach. So to conclude, this is a different approach to design radio transmitters. It has some advantages, it has some limitations, it has some work to do. So that's why we are here, and of course we are available. It will be a pleasure to collaborate with other groups. For example, in our case, it's some groups that can bring the expertise on the power amplifiers, on the filter design, that we can work together in order to proof of concept a complete solution. Of course, we welcome all those contributions. Thank you for your attention. Thank you.